Okay, let's see, files. Okay, so section 10.8. So first, okay, can you see it?
Yes.
Yes. So first we will discuss arc length for parametric curve. So we have a parametric curve which moves, let's say, from some point A to B, and what is the distance traveled between those points along the curve. So here is the picture. You have a curve which starts at the point t equal A, let's say here, and as t ranges from A to B, the curve looks like this, and we would like to compute how long is this red curve. So that's in 3 dimensions. This curve is in 3 dimensions, and we would like to compute how long is this curve when parameter changes from A to B. So we do this, we will derive the formula. You will be responsible only for knowing the formula. So at the end, after 2-3 slides, we will have a formula, and this is what you would have to use. But here is also the derivation. So what we do, we divide this curve by into some subintervals. Let's say this is T0 will be A, then some point T1, T2. We just kind of have different points on the curve. T0, T1, T2, Tn, Tn minus 1, Tn, or Ti minus 1, Ti, and the last point is Tn equal B. So you divide this, and then the distance between such 2 points on the curve, well, that's r at the point Ti minus position vector at the point Ti minus position vector at the point Ti minus 1. This gives you a distance of the segment which joins 2 points, 2 neighboring points on the curve. Of course, if r is f plus g plus h, well, this is, you put scalar component here. So this is f of Ti minus f of Ti minus 1. F is the first component of r. G of Ti minus g of Ti minus 1. G is the second component, and hti minus hti minus 1. H is the third component of r. And of course, then the sum, we will just compute the sum of those segments. Of course, the sum of those segments is not equal to the length of the curve, because you just have a finite number. So kind of just, when you have 1 point here and 1 here, that's a segment, and of course, this is a curve. But as number of points is getting bigger and bigger, of course, the sum of all those segments approximates this curve. So by definition, the length of the curve is limit of sum of those magnitudes of those vectors. Of course, this is not useful to use in computations, because you would have to kind of just put those points and divide everything and so on. So let's now try to reformulate this so we can use this for computations. So L is limit as number of points goes to infinity from 1 to n, magnitude of delta di, delta ri. So which is components here as well. We call those differences fti minus f of ti minus 1, delta fi, and so on. So with this notation, the arc length takes this form. Now, if you assume that the functions f derivatives, so have derivatives, and derivatives are continuous, then, of course, the difference between two neighboring points is the derivative at some intermediate point times the distance between two points. So one point is ti minus 1, another one is ti. The distance between them is delta t, equal distance. So delta fi is derivative at some intermediate point. Ti asterisk, asterisk means intermediate point, delta t. Same thing for delta gi is derivative of g at some intermediate point. Now, this intermediate point and this one may be different. So probably it would be better to put here some different symbol. So again, somewhat misleading. Ti asterisk here and ti asterisk here, those 2 points may be different. And similar for delta hi. Delta hi is derivative of h at intermediate point delta t. Again, all 3 points may be different. And of course, so now what is the limit of this? Well, so if you substitute, so instead of this, you substitute this. So you get limit of this thing, f prime square, g prime square, h prime square, and delta t square, you factor this out, delta t. And of course, you recognize that this is a Riemann sum. So as n goes to infinity, this goes to the integral. So the length of the function is integral as parameter ranges from a to b, and square root f prime square plus g prime square plus h prime square dt. Just a Riemann sum. So again, if you miss the derivation, don't worry. This is what you have to know. Arc length formula is here. L is integral from a to b, f prime square, g prime square plus h prime square dt. Now, useful shortcut notation, easier to memorize. So this is integral from a to b. Magnitude of the, of course, that's the magnitude of the tangent vector, r prime. Yeah, r prime, when you have a curve r prime is a tangent vector. So you have to compute magnitude of the tangent vector and then integrate this from a to b. Of course, you can check that this is equal to this, of course, but that's easier to remember. Now, arc length, of course, is independent of the parameterization. If you have different parameterization, you should get the same arc length. We are not proving this, but that's what is known. So here is a computational example. Again, it's just a routine application of arc length formula. Find the arc length of the helix. You remember we had this curve. 2 cosine t, 2 sine t, and t. If t would be 0, this would be a circle on the xy plane. But of course, t is not 0, so kind of just we are moving along the cylinder. Yeah? X squared plus y squared is equal to 4. So we are moving on the, this curve is on the cylinder with radius 2, and we call this curve helix. So this curve has a special name, it's called a helix, and we would like to compute how long is this helix as t ranges from 0 to pi over 2. So again, just direct application of the formula. So you need to compute the derivative of this. Well, of course, easy, component by component. So r prime of t is minus 2 sine t, 2 cosine t, and the derivative of t is 1. Okay, so arc length, using the formula on the previous slide, is integral. T ranges from 0 to pi over 2. Those are the limits of the parameter. Magnitude r prime of t dt. Well, so what is a magnitude? Well, magnitude is square root this square plus this square plus this square. So magnitude minus 2 sine square plus 2 cosine square plus 1 square. Well, so of course, if you take the square, this is 4 sine square plus 4 cosine square plus 1. Well, so you can factor 4. So this is 4 sine squared plus cosine squared plus 1 outside the parentheses. Of course, sine squared plus cosine squared, you know, that's a fundamental identity. This is equal to 1. So we have 4 times 1, which is 4, plus 1 is 5. So we have square root from 0 to pi over 2, 5 dt. Yes? Questions? Any questions? So if you integrate this, you have square root 5 and pi over 2 is the length of the interval. Again, routine thing. The principal unit normal vector. Next things. You have a curve. So here you have a curve, this black one. Of course, you can compute the tangent vector. Tangent vector is derivative of R. So R prime of t is a tangent vector. And then you can compute a unit tangent vector. So dividing R prime of t by the magnitude of R prime of t, we have a unit tangent vector. And the notation for the unit tangent vector is boldface T, uppercase T. Of course, this unit tangent vector depends on the parameter, kind of. It's changing. As you change the parameter, this unit tangent vector is different at each point. But anyway, so unit tangent vector, well, easy to compute. You compute the derivative and you divide this by the magnitude of the derivative. So that's unit tangent vector. Now, when you have a scalar product, dot A with the same vector A, of course, that's equal to the magnitude of A squared. Yeah, you remember, the magnitude of A was square root from this. So it's true for any vector. Now, of course, we know that the magnitude of this vector is 1. Well, so this means that the dot product of t with t is equal to 1. So we have this relation. The dot product of unit tangent vector with itself is always equal to 1. If you differentiate this, well, then you get t prime t plus t prime equals 0. Yeah, derivative of 1 is 0. This means that 2 t prime of t of t is equal to 0, or if you divide by 2, t prime of t times t of t is equal to 0. Well, what does this mean? This means that the vector t prime of t is orthogonal or perpendicular to the vector t. So that's the conclusion. The vector t prime, you don't see this t prime here. So t prime of t is perpendicular to t of t. And then, so it looks like this. So now, if you divide this t prime of t by the magnitude of t prime of t, that prime is missing. So kind of just when you review things here, this is n of t is t prime of t over t prime of t. For some reason, those primes kind of got absorbed in the letter t. So here, make a note. This is t prime over magnitude of t prime. So the normal vector is derivative of t prime and divided by the magnitude of derivative. So n of t is a unit normal vector, is perpendicular to t, and points in the direction where this curve kind of curves. So here, you see curves like this. So the unit normal vector points always in the direction where the curve is turning. So here we have tangent vector, we have normal vector. Tangent, they are, of course, perpendicular, orthogonal to each other. This is a picture in 3 dimensions because this does not look like a right angle, but it should be right angle here between this and this. So we have, so okay, so we can compute unit tangent vector, we can compute unit normal vector. And probably then next there's some kind of computational example. Let's do some specific example in a moment. But so any questions here?
I have a question, Professor.
Yes.
In what case in real world we would need to calculate, for example, the normal vector?
Well, you'll see a normal vector is related kind of to acceleration, kind of in mechanics and so on, kind of. So you need such things. So there's a lot of applications of this part of calculus to mechanics or physics. Equation of motion. So again, the normal vector is kind of has something to do with acceleration. Yeah, tangent vector has something to do with velocity, and so on. Kind of. So there's a lot of applications. Again, so if you are the engineering student, you'll have mechanics courses. If you have already mechanics courses, probably you saw this already. But usually you take those mechanics courses after you finish calculus. So you will see kind of just a lot of applications. Again, so one application is in mechanics, physics, velocity acceleration.
Yes, I've seen in physics, like the formula was kind of different. Yeah, that's why I was a little bit confused.
Well, maybe they're using different notation and so on, kind of the only thing. But certainly, kind of the calculus is the language of physics. And depends what kind of physics, okay? So just you see, if you have quantum physics, that's a different story and so on, kind of. But again, mechanics, kinematics, just motion. Again, tangent vector, it's related to velocity. Normal vectors will be related to acceleration in mechanics.
Okay, thank you.
So here the example how to compute the principal unit normal vector. Okay, so here we have the curve. R of t is cosine 2t, sine 2t minus e. So it's kind of also like a helix. Yeah, moves around the cylinder with radius 1 because x squared plus y squared, of course, is 1 by this basic identity. So that's kind of a variation on the helix. Okay, and we have to compute unit normal vector. So of course, you have to start first with unit tangent vector. You remember, unit tangent vector is r prime of t, r prime is tangent vector. And unit, you have to divide by the magnitude. Okay, and now computations, of course. If r of t is here, so what is r prime of t? R prime of t is minus 2 sine 2t, and 2 cosine 2t, and minus 1. Clearly, that's derivative. Well, so you need magnitude of derivative. So again, magnitude of derivative is square root, this square, so 4 sine squared plus 4 cosine squared plus 1. And as before, 4 sine squared plus 4 cosine squared gives you 4. And 4 plus 1 gives you 5. So that's a square root 5. So magnitude of r prime of t is always square root 5. So the unit tangent vector is r prime of t divided by the magnitude of r prime of t. So which is minus 2 over square root 5 sine, 2 over square root 5 cosine, and minus 1 over square root 5 because that's a magnitude. Now, we have to compute the unit normal value. We have to compute now t prime and the magnitude of t prime. So of course, t prime, well, you differentiate, again, component by component. So derivative of this is minus 4 cosine 2t over square root 5. Derivative of this is 4, minus will be minus, so minus 4 sine 2t over square root 5. And of course, derivative of this is a 0, that's a constant. So that's t prime. So of course, the unit normal vector will be this divided by the magnitude. So let's compute the magnitude. Well, so magnitude is again this squared, which is 16 over 5 cosine, plus 16 over 5 sine square. Of course, again, you factor 16 over 5, and cosine squared plus sine squared is 1. So this is equal to square root 16 over 5, which is 4 over square root 5. So that's a magnitude of the unit of t prime. So of course, the normal vector, by definition, you remember normal vector is just t prime. Here you see this prime, yeah. So t prime divided by the magnitude of t prime. So of course, t prime is here, is here. So you put here this, and this. And if you divide by the magnitude, you get square root 5 over 4. Now, of course, you still multiply this, and you see that 4 cancels, square root 5 cancels, and you get just minus cosine 2t minus sine 2t and 0. So that's the normal vector. Unit normal vector. It's written here normal vector, of course, that's a unit normal vector. Okay, there's one last thing. So-called binormal vector. What is binormal vector? Well, the binormal vector by definition, well, the notation is B, is cross product unit tangent vector and with unit normal vector. So if you compute the cross product of unit tangent and unit normal, you get binomial vector. Of course, you know that that the cross product is perpendicular to both this and this. So binomial vector is perpendicular to t and n. So it looks like this. This on the other way, kind of, yeah. So again, this vector t, n, and b, they are mutually orthogonal to each other. So b of t is a unit vector. Of course, it's a unit vector, yeah, because this is a unit vector and this is a unit vector. So if you compute the magnitude of this, that's also a unit vector. Yeah, you see, what is the magnitude of this? Magnitude of this is magnitude of t, magnitude of n, which is 1, 1, times cosine of the times sine, cosine of the angle between them, and angle is 90 degrees, sine angle. So angle is 90 degrees, so it's 1. Yeah, you remember this is the kind of the.
Sure.
Yeah.
Would the binormal vector, since that's the product of the unit principal vector and also t, I don't know what the exact semantic for that is, but that would be, I know it's perpendicular to both, so that wouldn't be parallel with t, right? That would be pointing like maybe upwards or downwards or something.
Correct. Yes, yeah. So kind of maybe go this way or this way, kind of just we see, well, depends kind of how the vectors t and n are looking. So maybe like this or maybe the other way. But it's still orthogonal to both of them.
Okay, thank you.
So again, it's unit for the, because what is the norm of this? Norm of cross product is magnitude of t, which is 1, times magnitude of n, which is 1, times sine of the angle. If the vectors are orthogonal, of course, the angle between them is 90 degrees. So sine 90 degrees is 1. So of course, the magnitude of b is 1. So that's automatically. You remember when we are computing unit tangent, unit normal, we had to divide by the norm. Here, this vector is automatically unit. It's just right away, it will come to be unit vector. And here is, again, computational example. That's the last slide from this part. Find the binomial vector b for this curve. So of course, this is the same example we had. So you remember we computed unit tangent, and unit tangent was here. So those computations were already done before. Yeah, again, if you can check it again, but we know that for this curve, we computed unit tangent vector, it's given by this formula, and unit normal vector is given by this formula. So of course, to compute the binomial vector, also I say binomial, binormal, yeah, that's kind of typical mistakes, kind of easy to say here instead of binormal, binomial, but it's binormal. So correct terminology is binormal vector. But again, easy to make the mistake and say binomial, certainly. So binormal vector is cross product of this times this. So of course, this is this 3×3 determinant, I, J, K. First, you put the components of this. So this is -2 square root 5 sine to t, 2 over square root 5 cosine to t, and -1 over square root 5. And of course, then you put components of this, minus cosine, minus sine, 0. And if you compute this determinant, well, you can verify that this is first component is minus sine to t over square root 5, second component is cosine to t over square root 5, and the last component is 2 over square root 5. So that's a binomial. Check, of course, that norm of this is 1. Magnitude of this vector, of course, is 1. Easy to verify. Square this plus square this, of course, gives you 1 over 5, and this gives you 4 over 5. So that's, of course, 5 over 5, which is 1. So magnitude of this is will automatically be, if you didn't make mistake here and here, magnitude of this will be automatically equal to 1. Okay, so this is 10.8. I would like to maybe to comment now on the some homework. Maybe we already discussed, I think, all homeworks up to 10.5. So maybe let me now, I will go and try to open the web work. Okay, so here's web work. So let's look at 10.7. Now there's a lot of problems, okay? 20. Maybe let's see, did we check to 10.5? Maybe I wanted still to first to look at 10.5. Yeah, 10.7 was today. So let's look at 10.5. So here I think even more, 22 problems, if I remember. Yeah, okay, yeah. So you see, so 10.5 is still open. You see, it closes on 7. There's a lot of problems, but 90% of them are just routine problems, just using some formula, some kind of basic things. I would like only maybe first, before we go comment or before we ask questions, I would like maybe to comment on the last problem, because there's some terminology which was not introduced when we discussed this section. So here, so that's the last problem in this section 10.5. I start from this because there's terminology which you may not be familiar with, perhaps. Well, maybe you can kind of guess the meaning, yeah, but kind of let's discuss it. So here is the following. We have two curves, R1 and R2 in space. Curve R1 is t squared, t cubed, and curve R2 is minus 5t plus 9, 16t squared minus 64. And then, of course, those two curves, there's some you can think that kind of they form some trajectories. Let's say kind of just, let's say you have a car and the car moves according to this rule, and a second car moves according to this rule, or maybe some object in space moves according to this rule, another object in space moves along this rule. And now you have to say, to answer whether or not those two paths collide. What does this mean, collide? Well, so again, if you have two objects in space, they collide when they reach the same point at the same time. Yeah, if you have two objects and they reach the same point in space at the same time, that's a collision. So this is what means the collide. Now, of course, the collide and intersection is different. You may have two curves, they may intersect, but they may not collide because, let's say, this intersection point, and you have two particles, and those two particles may reach this intersection point at different times. If this happens, they still will pass through the same point, but at different time. If this happens, there's no collision, but there may be intersection. So, of course, collision is a very strong property, intersection somewhat weaker property. So collide and intersect. Collide means same time, same point. Intersection means same point, but perhaps different times. So this is the difference in terminology. So again, we didn't discuss what collision means. Of course, intersection is clear what it means, yeah. But the collision means you reach the same point at the same time. So of course, so to answer whether or not they collide, what you do? Well, this means that first component must be equal to the first component, second to the second, and third to the third. So to collide, you have to satisfy three equations with one unknown only. So of course, that's not such a, it's a rare thing, yeah. So kind of just you have three equations: t equal minus 5t plus 9. Second equation is t squared equals 16t squared. And the last equation is t cubed equal minus 64. So you have to satisfy three equations for one unknown. This does not happen too often. And of course, you see lots of collisions don't happen too often. So kind of let's look at the solution. So of course, we have three equations. So let's see if this happens or not. So we have to satisfy three equations: t equal minus 5t plus 9, t squared equals 16t squared, and t cubed equal minus 6. So you see three equations at the same time. Well, the second equation implies that t equal to 0. That only happens, yeah, 15t squared is 0, so t squared is 0, t must be equal to 0. So second equation is satisfied when t is 0. And when t is equal to 0, of course, this is not satisfied and this is not satisfied. So this means no collision. Do not, so which means that the path do not collide. No collision. Any questions? This is clear?
Professor, does there need to be a solution for t, like the same number for t that satisfies all three equations, or do you just have to have?
Exactly. No, of course. The same number for three equations. Exactly. So you see, that doesn't happen too often. That's quite restrictive. Yeah. You have to have t which satisfies simultaneously three equations. The same t must satisfy three equations. Yeah, of course, you can solve this for t, you can solve this for t, you can solve this for t, but they are different. Because those t's are different, this means there's no collision. So collision happens when this system equation has solution. This system does not have a solution, so there's no collision. Now, intersection. Well, intersection means, so to get inside, let's consider those two curves, but let's change parameterization. Yes, the time may be different. So let's say this is, if you keep here t squared, t cubed, you put here instead of ts. So you have now two parameters, t and s. So for the intersection, you have to now, oh no, they just changed parameters in the first equation. So okay, let's change it here. So first curve is parameterized by s squared s cubed. Second curve by t. So intersection happens when again you have 3 equations and 2 unknowns. If this system has a solution, again we have more equations than unknowns, so kind of this also does not happen so often, but of course more often than here with collision. So kind of just now, kind of we will have intersection if you can find solution T and S, the same solution, the same S and T, which satisfies all 3 equations. So of course now you see kind of that trying to solve it. Well, from the 3rd equation, S is equal plus minus 4T. Well, if this is the case, if S is this, if you substitute it in the last equations, then you get that T equal plus minus 1. And we see that the one of the solutions satisfies the first equation. So it's kind of just one thing. So I think if T equal 1, we have minus 10. No, so if T is equal minus 1. So if T is equal minus 1, then of course all equations are satisfied. And so T equal minus 1 and S is equal 4, I think. Then you satisfy all equations. Yeah. So that is intersection. So those particles, let's say if this is movement of one particle, this movement of a second particle, they will reach the same point, but at different times. So there's no collision, but the path will intersect. Okay, so this is problem 22. You have any specific questions now? There's 22 problems. Somebody tried it, kind of, if you have some specific questions, maybe we can go and discuss it. But again, as I said, most problems, there's a lot of problems in this section, but most of them are more or less routine. Just applications of known formulas, dot product, cross product, kind of distance of the point from the plane, and so on, kind of. So do you have specific questions? Well, okay, that's okay. So let me just click on a few of them, and you will see kind of that they are really, really typical. Okay, so let me go. So let's click fast on some of them. So let's start 1. Okay, again, you see, so a lot of problems, but you have to just kind of just think a little. 2 lines parallel to the 3rd line are parallel. Yeah, probably yes. Yeah, if you have 2 lines which are parallel to the 3rd line, all of them have the same direction vector. So probably that's true. So kind of just solution for the first one is probably true. Let's see. True, yeah. Let's look at the last one. 2 planes orthogonal to a line are parallel. Yeah, if they are orthogonal to the same line, of course, just you see, this means that they have the same normal vector. So they are parallel. So probably it's true as well. So 11 looks like it's true as well, true. And more or less, all of those kind of questions are of this kind of difficulty. But you see a lot of things. So kind of just, you see, certainly you can get the full credit just guessing. Yeah. Just if you just put true, false, and so on, kind of, then you see you can check the answer and you can guess. But of course, try to understand things, because kind of then you will be ready for the test. Given the vector equation, R of t, write in terms of the parametric equation. Again, nothing to do. So x of t is 3 minus 3t, y of t is minus 3 minus 3t, and z is equal minus 2 minus t. Nothing to do here, just notation. So again, most problems are routine, as I said. Most, maybe there's 2 or 3 where you have to think a little, but most of them are absolutely routine problems. Next one. Vector, find the vector from the point A to B. Well, so of course, this is 4 minus 4, 0, 2 minus 1, 1, and minus 14. Yeah. And then you have to answer if this line is parallel to the line passing through those two points. So here, again, just let's look at the solution. So certainly the point is 0, 1, minus 14. So here, of course, you have here, this is the second point. This is the same vector. So of course, this line is parallel. So this is true. Yeah, this line is parallel to this one. And similarly, you can kind of argue for those others. Find the vector and parametric equation of the line through the points. So again, typical. The direction vector is a vector which we kind of, so it's here. Yeah, the direction vector is here, and the point is here. So of course you can write. So the equation of the line is P plus R plus VT, and then kind of just, you see, if you substitute, kind of just. Yeah. So again, so the R of t is minus 155 plus t minus 4 minus 35. Yeah. And then, of course, then if you compare kind of the first component, second component, third component, you will get parametric equations. So absolutely routine. Consider the line which passes through the point and which is parallel to the line. Well, okay, so find the point of view of the new line with the coordinates planes. So let's maybe only discuss how to find this line. So of course, to find the line, well, you have a point. And so what is the direction vector? The direction vector is the same as for this line. So direction vector is 3, 2, and 3. Or you can take, of course, minus 3, minus 2, minus 3 as well. That's okay. I think this is what they took in the solution for some strange reason. No, they didn't. Okay. So clearly, you have a point, you have a direction vector, so you can write parametric equation of the line. And now kind of just those intersections, xy plane. To find the intersection xy, the line will intersect the plane xy if z is equal to 0. So to find the intersection with xy plane, z is equal to 0. To find the intersection with xz plane, y must be 0. And to find the intersection with yz plane, x must be 0. So let's look at the first one. XY plane, so z must be 0. If z is 0, as you see here, t will be 4 over 3. And if you substitute it here and here, you can compute x and y. So that's how you solve it. Six. Again, routine. We have a point, and the line is orthogonal to the plane, which means that the direction vector is normal vector to the plane, which is minus 1, 1, and a minus 1. So you have, again, the normal, they already told you that this is minus 1 here. Yeah? So the normal vector is minus 1, x, so minus 1, plus 1, minus 1. Again, routine problem. So we just reviewed some of them. If you have, so I will not go over this web work problems anymore. If you have specific question, then maybe I will answer. But here again, it's very long section. You have 22 problems, but as I said, 90% of them are very routine, just application of known things. So this is all for today. Thank you.
Thank you, Professor.
Thank you, Professor.
So thank you. So see you Wednesday.
Thanks, G.